Welcome back. So we are learning about the Thevenin theorem, and now we are going to look at the circuits that have basically dependent sources. So earlier example that we did that contains basically independent voltage and current sources, and we have seen like how we can solve them, okay, by calculating the Thevenin resistance and Thevenin voltage, okay, and we can make the equivalent circuit. So now if we have a dependent source within our circuit, for example, here we have a dependent voltage source. So now because there are some limitation, okay. So the limitation is if we have only dependent source within our circuit, the circuit cannot self-start, okay, because that voltage source, for example, it depends on the value of current Ix. So the question is how the Ix is being generated in the circuit, okay. So for this case, because like it cannot self-start, what will we do? We will try to induce, okay? We will try to apply some external voltage, okay, external source. It could be a current source, it could be a voltage source, okay? So we will apply that, and by using that, okay, we will try to compute like what could be the voltage drop here and the current drop, okay? Now, always whenever we are analyzing that, because it cannot self start, okay, so we basically assume that, okay, our Thevenin, okay, or open circuit voltage is 0, okay. So this is the simplification that we use, okay. Now practically what we can do, we can use, for example, a voltage source. So use a voltage source and connect it across your load point, okay. For example, I choose a voltage source of 1 volt, okay. So now this is basically your Thevenin, okay. So our target is to find R Thevenin basically, okay. So R Thevenin is always basically what? Thevenin divided by the I short circuit, right? The current that is basically flowing through that circuit. So we will connect a voltage source. We will define any value of that. For example, we define that voltage source value is 1 volt. We can use any value, okay? And that doesn't matter, okay? So with that voltage source, we will calculate that how much current is basically flowing from that source, okay? So we call this IP, or like actually this could be the short circuit if this is short circuit. We compute that. So like we have a circuit here, we can apply different circuit analysis techniques, and basically we get that current IP, okay. So basically this circuit can be simplified to a form of R Thevenin. So once we have IP here, so resistance will be basically voltage divided by that current value, okay. So our analysis approach will be this one, that if you are putting a voltage source here, compute the current flowing from that voltage source, okay. So 1 volt divided by the IP, that will give me the R Thevenin resistance. If you want to use the current source, okay, the approach remains same. Like you can connect a volt current source here, okay, of any value. Typically we use 1 ampere. We can use, like if it is kilo ohm, you can use milliampere. Resistances are in kilo ohm, okay, or like you can use any value, okay, but typically we go with 1 ampere. So now I know this value of current, okay. Now my target is to find what is a voltage drop, Vp. So again, R Thevenin is basically voltage divided by the current. So the current we already know, this is 1 ampere. So basically once we find the Vp, we can find basically the R Thevenin. Okay, so this is how we will analyze the circuits with the dependent voltage sources or current sources. Now let's have a look at a practical example to see how we can basically apply this concept. So the question is here, find the Thevenin equivalent circuit at A and B. So Thevenin equivalent circuit means we want to find what is basically the R Thevenin. Like if I have a circuit, I can basically simplify this whole circuit between point A and B in the form of R Thevenin. Okay, so this is the purpose of getting the Thevenin circuit. Now our target is to get R Thevenin. Okay, so we learned that we have a basically dependent source here. It cannot self-start. So what we have to do, we need to put up either a voltage source or a current source here. Okay, so once we have that, so basically we need to calculate what could be the voltage here and what is the current flowing through that one. So if you know that, divide them and we get basically our RThevenin. So this is the target. Now the question is, we can use either a voltage source here or current source here. For example, I can put a voltage source of 1 volt here. Now I need to find the current that could be basically flowing from this point, right? So apply a voltage source here, and then you can simply, for example, apply nodal mesh analysis techniques and find the current here. So once we have that, we can get the results. Okay, so let me solve this, okay, by basically putting a current source here. Okay, so the choice is basically sometimes depends on the circuits that you have. So choosing one can make the analysis more simple. For example, if I use a current source here for this case, it will make my analysis more simpler as compared to the voltage source. So let's assume that this current value is 1 ampere. Okay, so again with the assumption like we just earlier make, okay, whenever we have a dependent voltage source only, our Thevenin is always 0. Okay, so that's why like we get kind of a short circuit, okay, for that case. All right, let's come back here. So IP is 1 ampere. I connect this current source here, and now I want to find basically what is the voltage drop across this connected source. So actually what is the voltage drop basically across 2 kilo ohm or like this node A. Okay, so if we get basically the voltage drop at node A, that will give me basically the voltage drop across this one. Okay, so for that, what we can do here now, our target is to get that. We can apply any technique, okay, to get that. For example, let's try the nodal analysis here, okay, because we know that this is the voltage source. This could be one node. Let's call this V1, and this is basically second node. Let's call this VA, okay, which is basically our desired one. Let's write the nodal equation at the V1. So what will be that? All currents leaving, right? So this current is leaving. What will be that? V1. Okay, this is the nodal equation at V1 minus voltage drop here. What is the voltage drop here? Okay, 2000 of Ix divided by 2K plus this current leaving, that is basically Ix, right? So V1 minus 0 divided by 1K plus this current leaving, that will be basically V1 minus VA divided by 3K is equal to 0. So here we have a basically dependent variable, okay, which is Ix. So Ix is basically what? If you look at this, Ix is nothing. Ix is the current through this one. That will be V1 minus 0 divided by 1K. So basically V1. I can put this value, okay, in this equation. So that will give me what? It will give me V1 minus this 2000, this is 1000. Okay, so 2000 divided by 1000, that will give me 2, right? So 2 V1 divided by 2K, right? So 2000 times V1 over 1000. So 1000 and 2000 will be cancelled, that will become 2. So 2 times of V1 plus V1 divided by 1K plus V1 minus VA divided by 3K is equal to 0. So we can multiply this whole equation with the 6K, okay, just to make our analysis equation simpler. So if you multiply with 6K, so 2 and 3, 2 will be cancelled by 3. So 3 times of V1, okay, so basically V1 minus 2V1, that will be minus V1, right? Okay, so this will be minus V1, so minus V1 times 3, that will be minus 3V1. Then I have 1, that will be 6V1. Then 3 and 2, that will be 2V1 minus 2VA is equal to 0. So I'm just rearranging the equations, okay? So 2 plus 6, 8V1. So not 8. Okay, we have basically 2 plus 6, 8. Then minus 3. So 8 minus 3, 5. So basically 5V1 minus 2 times of VA is equal to 0. So this is basically the simplified nodal equation for this. Let's write the nodal for VA. So for VA, which current is leaving? This current is leaving. What will be that? that will be VA minus V1 divided by 3K. Then this current is leaving, what will be that? VA minus 0 divided by 2K. Then this current is leaving, what is that basically? Minus 1 is equal to 0. Okay, so again we can multiply with the 6. So what will I have here? Just to simplify this one, 6K. So 2 times of VA minus 2 times of V1 plus 2 and 3, 3 times of VA. So this minus 6 is equal to 0. Okay. So again minus 2 V1, 3 plus 2, 5 VA. This will go to the other side. So that is basically 6. So I have basically two equations, okay, and two unknown. Okay, so what is the second equation? Minus 2 V1 plus 5 VA is equal to 0. So two equations, two unknown. Okay, so if you just simplify these two equations, okay, we can get the values of V1 and VA. Okay, so simplification, okay, you can do substitution, whatever technique. So if we simplify this one, basically the value of VA, it comes out to be 10^7 volt. Okay, so VA is basically this voltage, okay, which is our desired voltage. Okay, so if we have VA is equal to 10^7 volt, okay, you can also get V1, but I'm not writing here because our focus is just like VA, because VA is basically same voltage as VP. Okay, so we got basically our desired VP here. Okay, IP we already know that, so it means I can write using this. Okay, now using this I can write that our Thevenin basically will be equal to what? VP, which is 10/7 divided by IP, which is 1. So actually 10/7 ohm. So this is 10/7 ohm. This is the basically Thevenin equivalent circuit. Actually the computation of our Thevenin for this circuit. Okay. So because we use a value of 1 milliampere actually. So basically milli multiply with 6K become basically 6. So 1 milliampere here. So it will become 10 kilo. Okay, so that will be the only difference. Okay, so milli was basically added to cancel out the impact of kilo here. Okay, so 10^7 kilo ohm, that is basically the Thevenin between point A and B for this circuit. Thank you so much.